We'll now look at this question, which is relating coefficients of powers in an expansion, and they want you to prove certain things. So these are questions that are called binomial identities, and we often talk about the fact that there are different types of these identities. And in this particular case, you're asked to show a whole bunch of coefficients is equal to an expression over here. And this is what we'll call a sort of type 1, or unofficially, we'll call it a sort of type 1 question, as opposed to, and there's a certain way we'll deal with those questions. So let's see what the question is saying here. You've got the coefficient of x to the k in the expansion of 1 plus x power of n, where n is a positive integer, is denoted by ck. In other words, they're using this notation ck to represent nck, but it's really the same thing. And so with a bit of binomial, you should be able to expand this out, and then you'll know what that means. And then they want you to show C0, which is NC0, plus 2 NC1, plus 3 NC2, plus dot dot dot, plus n plus 1C, n plus NCN equals n plus 2 to the n minus 1. So this is an example of a more difficult question, especially when it's not led through, but it's still ultimately a whole bunch of C's, NC's on like combinations on one side. And on this side, there's no combination. So it's a type, what we'll call a type 1 question. It's an algebraic identity without combinations. So the way to do that is always the same. You're basically going to find an appropriate identity, which they've kind of given you already, and then sub in and value for x. That's the simple version anyway. This one's a little bit more involved. Okay. And then this one, you now want to find this sum. And you'll notice that on the left-hand side, it's again a whole bunch of NC's with some denominators. And again, it's a bit more involved than the standard, but you're still ultimately a type 1 question, and you want to actually find the sum. So you actually want to find a expression on the right-hand side, which will give you this sum. Okay. So this is an example of a much more difficult example of a type 1 question, but the method is exactly the same. So we will start with 1 plus x power of n. Now, you should be comfortable, especially when you're getting to the stage of doing these questions, of using the binomial theorem on these, and that will give you nck x to the k. That should hopefully be something you are familiar with at this point in time. If you're not comfortable with sigma notation, then you can think of that as nc0 plus nc1x plus nc2x squared plus dot 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 plus nck x to the k plus dot 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 plus ncn x to the n. But it will be very helpful to be comfortable with sigma notation when you're doing these sort of questions. So given the fact that 1 plus x to the power of n is equal to this, what I will firstly do is I will sub x equals 1. I mean, this is an expression that works for all values of x. So I can just put in a value of x. So that means on the left-hand side, I've got 1 plus 1 to the power of n. And that must equal the sum from k equals 0 to n of nck 1 to the power of k. I mean, 1 to the power of anything is just 1, right? Or in other words, I'm just going to get nc0 plus nc1 plus nc2 plus dot 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 plus nck plus dot 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 plus ncn. In other words, I've said nc0 plus nc1 plus nc2 plus all the way to ncn has to equal 1 plus 1 to the power of n, which is obviously 2 to the power of n. And so I've got one result there. You can either think about it in the expanded form or in the sigma form, either or. But that's a result. Is that what the question asked me to do? No, it isn't. Is there a reason I did that? Yes, there is. But as I said, this question is a bit more complicated. We're going to first need to get that. I mean, there's more than one way to do the question, but the way I'm doing it. And then because of the more complicated question, the other thing with these type 1 questions is that this identity might not be enough. You might need to modify this identity. Now, if you take a look at what you're trying to prove, and this will lead into type 2 as well, part 2 as well, you're trying to prove not just a whole bunch of NC's, but you want a coefficient in front of them. You want a 2 times, a 3 times, a 4 times, a 5 times, and n plus 1, not times. which suggests you want a number in front. And essentially, that generally suggests that you want to derive it. So if I take this expression I have up here, and now I derive this, that means I'm deriving the left-hand side, which is quite clearly going to be n x plus 1 to the power of n minus 1. That's pretty clear. But I mean, the left-hand side is equal to the right-hand side. So if I derive the left-hand side, the derivative of the left-hand side should equal the derivative of the right-hand side. So it must equal the derivative of the sum from k equals 0 to n of nck x to the k. Now, that might be a bit, I mean, if you're comfortable with similar notation, just use that. But if you're not, then it might be helpful to look over here. And that's basically deriving this thing here. But what that basically means is the first term's going to go, there's no x. This x is going to go, and I'm just going to be left with nc1. I'm going to be left with nc2 with a 2. So I'm going to have 2 times nc2 times x, of course, x to the power of 1. I mean, if I have an x cubed, I'm going to have 3 times nc3, x cubed becomes x squared, and so on. I'm going to get a k, nck x to the k minus 1 for this term, as an example. And then my final one, of course, is going to be n ncn x to the n minus n. That's what I'm going to basically be getting. Okay. So now that I know that, I have a new identity. My new identity is n x plus 1 to the n minus 1 equals nc1 plus 2 nc2 x plus 3 nc3 x cubed plus dot, 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 plus n ncn x to the n minus 1. This is my new identity. I have taken my initial identity and modified it, in this case derived it, to get another identity, which is still true. This is still true for every value of x, right? If the left-hand side is equal to the right-hand side, when I derive the left-hand side, it has to equal the derivative of the right-hand side. So since it's still true for all values of x, I'm still free to pick whatever value of x I'll sub. And just like the fact I subbed x equals 1 before, which is a key step when you do these questions, I will sub x equals 1 in here again, and that will give me n times 1 plus 1, I mean that's 2 to the n minus 1, equals, well, if I sub in 1, all the x just goes. So it just gives me nc1 plus 2 nc2 times 1, which is really nothing, times 3 nc3 plus dot, 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 plus n ncn. So at this point now, I have this identity as well as this identity. Is this what the question asked for? No, it isn't. Is this what the question asked for? No, not really either. But is there a reason why I did that? Well, yes. Let's write those two expressions out. We said it was n2 to the n minus 1. So that's what we've worked out at this point. Well, actually, I won't bracket that yet. Remember what we're trying to prove. We're trying to prove that nc0 plus 2 nc1 plus 3 nc2 plus 4 nc3 plus dot, 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 plus n plus 1 ncn equals n plus 2, 2 to the n. So that's what we're trying to prove here. 2 to the n minus 1. And so right now we've got these expressions, nc0 plus nc1, plus nc2 plus dot, 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 plus ncn plus ncn equals 2 to the n, and this. We want to get here. A little bit of examination may sort of reveal something. You might want to think about how we might want to use those. And it might actually make it a little bit more obvious if I do this in particular. In other words, let me move the NCN to the right. So let's write out NC3 as well. So if you look at this NC0, I've got NC0 and no NC0 here. If I've got NC1 and an NC1, I've got NC2 and 2 NC2, which I guess together will give me 3. I've got an NC3 and a 3 NC3, which together will give me 4. In other words, I'm really saying if we take equation 1 and add it to equation 2, we will get exactly what they are asking for, at least on the left-hand side, right? NC0, NC1 plus NC1 is 2 NC1, NC2 plus 2 NC2 is 3 NC2, NC3 plus 3 NC3 is 4 NC3, NCN plus n NCN is n plus 1 C NCN. So that means if we add 1 and 2, the left-hand side matches. Well, then the right-hand side will equal 2 to the n plus n times 2 to the n minus 1, which remember is, 2 to the power of n is 2 times 2 times 2 times 2 n times, which is 2 times, 2 to the power of n minus 1, right, which is n minus 1 times. You can just take out 2 to the n minus 1, and you're left with n plus 2. And therefore, we can prove that NC0 plus 2 NC1 plus 3 NC2 plus blah, 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 plus n plus 1 NCN must equal n plus 2 to the n minus 1. And that's the part, which basically is, as we said, a type 1 question, but where the key steps are identify your identity, modify it if required, and sub-evaluate. That's basically how you do it. In this case, there's a few steps. Take a first one, sub-evaluate, modify it, sub-evaluate, and then put them together. But that's just the nature of the question. So you'll expect this to be towards the end of a 3-note paper. When it's not lead through, it's probably equivalent to the last level of, last question kind of difficulty. And the next one is also quite similar in the sense that it's still going to be a type 1 question, but we're going to be asked to do this. We want to find this.